Okay, hello. So today we're doing exponentials. This is chapter 9.1. So we're just going to be focusing on evaluating exponential expressions and manipulating exponential expressions. And so this is a review for most of you, I hope. We're going to get to some novel calculations you can do, but most of this should be kind of review for you. We're just setting the tracks for when we start talking about exponential expressions. I'll get more into that in a second. So, like I said, hopefully this is review. If it's not, it's covered in greater detail in an earlier chapter of the book. Let me see. They go into it in a lot of detail in chapter 5? No, right before we started. Linear quadratic equations. Rational expressions. It's in chapter 4 somewhere. They do a lot about exponentials and exponents. Okay, 3.3. Yeah. So if you need more detail than what's in the book or what's in this video, chapter 3.3 will do you as well. Essentially, it's on both. This particular video that I'm trying to make is a little bit comprehensive. Hopefully, if you're a little bit shaky or you don't know how things work, it'll suffice. But there's always more stuff. Pretty much what's going to happen is I want you to have this material down. So we're going to cover all the basics, but this video is going to be super long because there are lots of basics to cover that I want you to have mastered. So by the end of this video, you should know some. We're going to start by introducing the whole lesson, which is chapter 9 and chapter 10. Exponential and logarithmic functions. I'll blurb a little bit about that, so maybe you'll have a little bit of context. And if somebody comes up onto your street and says, when do you see a logarithmic function, you'll be able to say, oh, I heard about it on this one. We'll get into more detail as the lessons go on. Then we're going to be talking most of the episode on evaluating exponential expressions. This can be done on the calculator or it can be done with pen and paper. And I want you to learn how to do both, in part because the calculator is not going to do it wrong, but also in part because I need you to understand how these things go together so that we can use the properties a little bit later. So you need to know how to use both ways, and so we're going to spend a bit of time talking about evaluating things. That's not what I want. Then we're going to spend the bulk of this lesson talking about combining algebraic expressions. That's what this medicine wheel is all about here. Essentially, if you have two terms that are multiplied together, you can combine their exponents in different ways. So we're going to talk about that quite a bit, and then we're going to be doing some activities where you combine algebraic expressions. Most of the worksheet for this particular lesson will be based on doing this simplification activity. We'll get to it when we get to it. Let's begin. Okay, so we've spent a lot of time talking about function theory, you know? Hey, what's a function? What does it do? What doesn't it do? Let's talk about domains. Let's talk about ranges. Let's talk about inverses. All that stuff, essentially putting the groundwork, I mean, in part because you're going to see a lot of it in calculus, but also in part because a lot of the rest of the course, we're dealing with functions that are more abstract than the ones we've been dealing with. Up until now, we've been dealing with, polynomials, 3x to the 4 plus 2x, something like that, right? Where you can evaluate the function directly. You can say, when x is equal to 2, what am I doing? X equal to 2, and you can substitute it in, and you can do the calculation. Calculate the number straight off. We're about to get into the world where you can't. For the most part, for most numbers, you can't grind out the value. It's possible to do it. I mean, our forebears in mathematics figured out ways to calculate these numbers, even if they're really weird, but it's kind of like to calculate these numbers for any possible input, you have to use all sorts of really weird and, kind of irrelevant to us procedures. In this series, lesson 6, so this is going to be a bunch of videos. I'm going to make some this weekend and I guess some more next weekend. But lesson 6 is focused on exponentials and logarithms. Which are two types of functions. They're more abstract, like I said, than the other types of functions, but their properties can be understood in terms of what we've explained so far and in terms of their own properties. So over the next couple of videos, we're going to be talking about the properties of these functions, but before we even do that, it's helpful to know that there's a reason for doing all of this. So I wanted to just to overview, just for a couple minutes, what the properties are, where you see these types of functions and what they do. So exponentials are functions that double regularly. That means they're always doubling. So you see them in systems like, you know, weeds, populations. You know, where first your lawn has weeds on it, and then the next week yours and your neighbor's lawns, and then there are 4 lawns with weeds in them, and then there are 8 lawns with weeds in them, right? And day 1, day 2, day 3, day 4. So day 1 there might be 2 weeds, and day 2 there are 4 weeds, and day 3 there are 8 weeds, and day 4 there are 16 weeds. Every time a regular time interval passes, the value doubles. Okay? So you see them in weed populations, but not just weed populations, no one cares otherwise. You see them in epidemics. You see the critical failure. Critical failure. In a type of, it's called cascade breakdown. You see it? Where one thing turns to 2. You see it in something called radioactive decay. All sorts. It's a pretty common type of function. So the long and the short of it is, one of the big applications for calculus and calculus-like courses or science was where the behavior of the system changes at in an exponential fashion, and exponential evolution has a really telltale behavior. It does this doubling thing. It's a little bit more specific than that, or it's a little bit more general than that, but if you think of it as doubling, then that's sufficient. So that's the point to exponentials. That's why we spend so much time on exponentials, is because it does that. Now, so what does an exponential function look like? Well, it's going to be a function of, so this day is going to be your variable, and the weed population is going to be your output. And so 2 to the x. That's just an example. We call expressions like that exponential functions. Okay. So what about logarithmic functions? You actually see this. You see this in a lot of weird, fun places. The deal with logarithmic functions is, instead of doubling, it takes twice as long to accumulate the same amount. It takes twice as long to double each step. Right? I guess so. One example is, well, hold on. Twice as long. Twice as x to double y. So for instance, logarithmic functions look like this. Log, say 2 of x, and this function looks like this. When y is equal to 1, x is equal to 0. 2 log of, hold on. Let me write it out like this. 0, 1, 2, 4, 8, 16. So y is equal to log of 2 of x, the value of y corresponding to this. So log 2 is 0, log of is 1, log of 4 is 2, log of 8 is 3, log of 16 is 4. Okay, so the idea here is the amount, delta x, the amount it takes to go from each step, y goes up by 1. 1, 2, 3, 4, 5, right? And the distance between each of these values of x corresponding to those outcomes doubles each time, right? So this distance here is 1. The distance between 2 and 4 is 2. The distance between 4 and 8 is 4. The distance between 8 and 16 is 8, right? So logarithms don't seem like you would see them very often, but they're actually pretty prevalent. So like the brightness of light is a logarithmic scale. So if somebody talks about the how bright it is, usually they do so using a scale that doesn't depend on the energy that's coming in. It depends logarithmically on the energy. So if it's 10 times more energy, the light indication goes up by 1. Something like that. A really famous logarithmic scale is the Richter scale for earthquakes. So, you know, the difference between 3 on the Richter scale and 4 on the Richter scale, and the difference between 5 on the Richter scale and 6 on the Richter scale is an order of magnitude. So, you know, the energy in that case goes up by a factor of 10, or the shaking goes up by a factor of 10, right? So if it's 6 on the Richter scale, that's 10 times worse than 5 on the Richter scale. But if it's 7 on the Richter scale, then that's 100 times worse than 5 on the Richter scale. That's another logarithmic scale. Musical notes are a logarithmic scale. So if you're describing the notes, so usually when we talk about musical notes in you know, in the European tradition, we do it in terms of letters A, B, C, D, and E. But if you look at them in terms of frequency or wavelength of the sound vibration, or the length of the string you need to make that note, the relationship is logarithmic. So going up 1 octave doubles the frequency. I think that's it. My favorite is like levels in video games. I don't know if you play role-playing games, or like say Pokemon Go. You know, it takes a certain amount of experience to go from level 0 to level 1, and then it takes twice that amount of experience to go from level 1 to level 2, and then it takes twice that much experience to go from 2 to 3, and then it twice that much to go from 3 to 4, right? Or that many hours catching Pokemon or whatever. And so, yeah, so the idea is at the very start of the game, when you're weak, you level up really fast, but then as time goes on, it takes you longer and longer to get to the higher levels. So you actually see logarithmic functions a lot in society in all sorts of weird places. It's really convenient for reasons we'll talk about, but essentially logarithmic functions allow you to express really, really big numbers in terms of really viable smaller numbers. So if there's a wide range of behavior in your data, logarithmic functions allow you to express that really, really wide and really, really bonkers behavior in terms of a really small output set. Anyway, so the long and the short of it is we're going to actually spend a ton of time learning about how to use these different functions. So before we can go any further, we need to talk about exponentials, the simplest. And like I said, hopefully, I'm really, really hoping that this is all review for you. A lot of it we showed up in a lot of the stuff that we did showed up as algebraic tricks that I kind of expected you to know in your polynomials, and we were talking about roots and stuff. You saw this notation. That said, the reason for the notation and the reason for how the notation works, the algebraic rules behind the notation, might not be clear to you, even if you know how to do it really well. So the purpose of this video is to sort out all of the business of where that exponential notation came from. Okay, so you have seen expressions that look like this. the minus 2, say 8 to the 2 over 3, or even 7 to the 2 to the 3. You might have seen expressions like this in the course so far. I mean, I believe that you have. We've been talking abstractly about expressions that look like this in polynomials, right? You say, okay, we've got a function that looks like that. Yeah. Or we might say, oh, the square root function, and I'll just tacitly, you'll see me write it like that. That's that notation. Okay? So we want to talk about generally what these expressions mean and how to evaluate them. So I just wanted to do a review just because I know people are kind of shaky on it. So to start, these are all expressions. They're all numbers. Okay. And they're all numbers that have a very specific shape. The form of the expression has a really simple shape. It's a to the power p, okay? Where a is a number and p is a number, okay? We call this number on the bottom, the big one, we call it the base. And we call the number up there, we call it the power, or we call it the exponent. I don't know why we call it two different things. In polynomials, we usually refer to it as the power, but in exponential stuff, we're going to call it more and more, we're going to refer to it as the exponent. So in this video, I'll try to go back and forth between the two. Every time you see the word power, think exponent. Every time you hear the word exponent, think power. Just keep it in your head. I'm talking about the same thing. If at the end of the video, things don't make sense, maybe rewatch it, and you'll hear me say this, and you'll say, oh, I see what they're talking about now. Right? So 3 to the 5, the base is 3, and the power is 5. Yeah. In 4 to the 1/2, the base is 4, and the power is 1/2, or 0.5, whichever you like. In 8, 2 over 3, oh no, let's do the other one. 3 to the minus 2. 3 to the minus 2. What's the base and what's the power? Base is the number 3. Power is minus 2. Negative 2. Okay? So, the thing about these here is that the base and the power, really they can be kind of any numbers, but I say kind of with a with an asterisk on it. This power here can clearly be any type of number. Right? You can have a whole positive number. You can have a whole negative number. You can have a fraction. You can have a negative fraction. Okay? The base, on the other hand, can it have any value? The short answer is, well, it depends on the context. Sometimes it can have any value, sometimes it can't. So, sometimes any number. And I'm gonna let's elaborate on that, right? So, for instance, can it be a positive number? Sure. Can it be a number smaller than 1? Can it be a fraction? 1 over 2 to the power 3? Sure it can. That's short for 1 over 2 times 1 over 2 times 1 over 2, which is 0.125. It's just a number. It can be a fraction. Fine. Can it be a negative number? Can the base of our term be negative? Well, the short answer is it depends. I'm really trying to emphasize the sometimes because I don't want you to get too weirded out on this. What a different number. 3, right? 1, 2, 1/2. So this is shorthand for a minus 2 times minus 2 times minus 2, which is equal to 4 times minus 2, which is equal to minus 8. It's a number. Fine, cool. It's just a number. Whatever. The second one, though, it doesn't exist. If you take out your calculator, you can hear me do my calculator business here. Yeah, calculator. You enter, I mean, we recognize that this thing is the square root. So you go square root of minus 2 on your calculator, and the calculator says error, right? So that term doesn't exist. So whether or not the base, clearly the power, the exponent can be any number, but the base can be any number. It really depends on what the power is. Sometimes the answer is yes, sometimes the answer is no. Okay. I want you to get a calculator out. It's really important that you have a calculator for the rest of the term. Get a scientific calculator. They sell them at the bookstore for like 10 bucks. Really good ones. I really like my Sharp EL510RN. If you borrowed one from me in class, it's that type. It's a really good scientific calculator. The reason I like it is that it doesn't, like, older fashioned calculators only show one number at a time and they don't accept symbols. So you learn how to do calculations and you kind of have to have it broken down in your head. It's actually a pretty good teaching tool, the older fashioned calculators, but it's really, really annoying. The nice thing about this Sharp calculator is that you can use, you can enter expressions into it. Like you could say, hey, Sharp calculator, square root of 3 plus x, 3 plus 4 minus 7, and then press enter and it will tell you some number. So I really like this one. If for any reason you can't find a calculator, if you can't afford one, if you can't borrow one for the rest of the term, come talk to me. We can sort it out. But it's really important that you get your hands on a calculator and that it live inside your pocket or bag for the rest of the term, because we're going to use a lot of it in the coming weeks. Okay, so now let's talk about how to evaluate expressions like this, 4 to the 3, on your scientific calculator. So there is an expression on my calculator, and you might have to look it up on yours. The reason I'm telling you to get the Sharp EL510RN isn't just because it's a cheap calculator, and isn't because it's I think it might be the cheapest one the bookstore sells. It's also a really good calculator. But the reason I want you to get it is because it's the same as mine, so I'll have an easier time telling you how to use yours. I can always give you advice, but advice on the ones I'm used to is the easiest. So I have a button on my calculator that looks like this. Y to the X. That's the button that you use to evaluate these numbers. And the way it works here is, first you press, first you press the number, say I want to evaluate this expression here. First you press the number 4, and then you press, and then the screen says 4. And then you press y to the x, y to the x, and that makes the screen go 4 up. See that little up arrow sign? It's just a little triangle. Yeah, that means that's shorthand for power or exponent. You see it a lot in computer science. And then what I'm going to do after that is I'm going to press the name of the exponent. So after that, I press 3. And the screen now says 4 up sign 3, which is the calculator's way of writing this number out, that expression. And now I'm going to press equals. And then that makes the calculator evaluate it, and the calculator says 64. It's really important to me that you learn how to use your calculator to evaluate these things. If it's a really, really different calculator, you might have to Google it, Google the instructions for how to enter exponents like this. But every scientific calculator should be able to do it. So, like I said, it's really important to me that you learn how to do this. So we're going to walk through how to enter in a bunch of different calculations. I'm going to use the same thingy where I'm like press. So let's try and I'll tell you what it says on my screen because I want you to walk through it. So what if it's 12 to the power 0.25? Okay. So first I write 12, and the screen says 12. And then I press y to the x, and the screen says 12 uppy mark. And then I go 0.25, and the screen goes 12 uppy mark 0.25, and then I press equal sign, and the answer is 1.8612. Did you get the same answer? Okay, let's try it for negative numbers. I'm going to expand this out a little bit. Okay, so what about 2 to the minus 4? Okay, how do I enter that in my calculator? First I'm going to press, get out of here, you. Okay, first I'm going to press 2, that's the base, and the screen says 2. And then I'm going to press y to the x, and the screen goes 2 uppy mark. And then I'm going to press the negative sign. So the negative sign on my calculator is different than the minus sign. The negative sign at the bottom looks like this. And that means put a negative number in, minus. Okay? And then I'm going to press 4. Because I'm trying to enter this part here. So screen goes here. What does the screen say before I press 4? The screen says 2 uppy mark minus. And now I'm going to press 4 and it goes 2 uppy mark minus 4, which is the calculator's way of saying this number here. Then I press equals and it spits out the answer, 0.0625. Okay, did you get the same one? All right. So before I go any further, I want you by the end of this to be able to evaluate expressions like this: 2 over 3 to the minus 4 over 7. Let's say your calculator knows how to do these. One way to do it really efficiently would be to evaluate each of these as numbers. So this would be 0.66666, and then minus 4 divided by 7 is minus 0.514, and enter those in. But I'm going to teach you on the more advanced calculators. I know the sharper calculators specifically, they know how to write it using parentheses. So it's worth going through that material. How do you use parentheses? Okay. So delete. So to enter this into the calculator, I'm going to use parentheses, and I'm going to do it in 2 parts. The first part, I'm going to try to enter this, the base, all as one expression. And the second part of it, I'm going to write this, the exponent, all as one expression. So to do so, I'm going to use the open close parentheses. So first I'm going to press the open. Oh, wait, that's not it. First I'm going to press the open parentheses, and that's going to make the screen go, or open parentheses, and the screen goes blah. And then I'm going to go 2, and the screen shows blah 2. And then I'm going to press the division sign, and the screen will go, hold on, 2 divided by, so then it looks like 2 divided by, and then I'm going to add the denominator, 3. So it goes that 2 divided by 3, and then I'm going to close parentheses. 2 divided by 3. That's my base. I'm using parentheses super carefully here. And now I'm going to go to an exponent. Oh no. Y to the x. And so the screen now says 2 divided by 3 uppy sign. And now I'm going to go open parentheses again. So it goes 2 divided by 3 uppy sign, open parentheses. And then I go negative. So it'll go 2 divided by 3 uppy sign minus so then I go 4, and the screen goes 2 divided by 3 uppy sign minus 4, and then I press division sign again, so it goes 2 divided by 3 uppy sign 4 division, and then I go 7. So then it says 7 in close parentheses. 2 divided by 3 uppy sign 4 divided by 7 close parentheses. And then I press equal, and the thing says 1.26073. Okay? So, that's essentially the procedure. I am able to express this whole expression by essentially breaking it down into parts using using parentheses. First the base. Tell it to calculate the base first. Then I use the uppy sign, and then I go minus 4 divided by 7. Okay? And that'll give me the right answer. So I want you to try it a couple times. I'm not going to do this breakdown where we I tell you about the uppy sign anymore, but I do want you to try it a couple times because learning how to do this is super important. In part because we're going to be teaching you how to do algebra, and I want you to be able to check your answers. So minus 6 to the 2, and 4 to the 1/2, and 9 to the minus 1 over 3, and 2 over 7 to the, how about minus 2 over 7 to the 6. So try to evaluate those now on the video. Maybe pause the video, give it a go. So this is 36. That's 2. This is 0.48075, and minus 2 divided by 7 are 6. That's 0.00054399. Okay. So hopefully you figured it out. It's not that hard once you figure out how to do it. It's super important that you're able to do it though for what's coming next, which is we're gonna be algebraically manipulating things. All right. So. As far as the calculator is concerned, it can evaluate as well as anybody else. I mean, there are some constraints over what the value of a can be, right? You know what? Let's add another one to this just to show you. How about minus 3 over 5 to the, oops, to the 2 over 5. One more. Try that one. Minus 3 over 5 all to the power 2 divided by 5. It says error. And that's because this one can't be evaluated because it's got a root in it and it doesn't like that. Okay, so the deal here is your calculator knows how to evaluate expressions like this. But I want to emphasize something here. It's not sufficient to go through life just relying on what a computer tells you is good or bad. It's really important that you are able to suss out the reasons why. In part because computers aren't infallible, in part because when they make mistakes, it's helpful to be able to pick out those mistakes, and in part because you have dignity as a human, and you deserve to use that dignity to demand, essentially, that you understand what's going on. There's nothing in this world that's created by somebody that you can't understand yourself. Have some dignity. So, we want to know why the calculator's coming out with these numbers. You know that if you plug in these numbers into the calculator, you get a number out. What do they correspond to? Why? How could you calculate? If you were on the deserted island, could you calculate these values? How do you figure them out? The key point in all this is how p fits into the picture. Because p can be any number. That exponent, that can totally be any number. Be a whole positive number. You know, like 1, 2, 3, 4, 700. Whole positive number. It can be a whole negative number. Like -2, or -8, or -500, right? The calculator knows how to calculate them. It can also be a fraction. Simple fraction like 1/2, or 1/8, or 1/90, right? And it can also be a mixed fraction. So 3/7, or 25/4, right? So how do you calculate these values? So we're going to essentially work through how to go from a basic understanding. I believe that you totally know how to do these in your head. Well, maybe not in your head, but I believe you know how to do them. We can go from talking about these whole positive numbers, what they mean and how to interpret them, into building a system where we can interpret these ones, we can interpret these ones, and we can interpret these ones. And the arguments that take us through this procedure are really cool because they kind of mirror how humans' understanding of what numbers are and how they mean is an interplay between what we're using the numbers for and the rules that we see the numbers following. So, I mean, don't worry too much about it. The long and the short of it is, by the end of the video, hopefully you'll understand how to interpret these, and how to interpret these in a consistent way, in a way that makes sense. So, positive whole numbers. Oh. This video is literally after the after the third assessment, which means if you're watching it, you probably have done a lot of polynomials up until now. And so I know that you can tell me how to figure out what the value of this number is. It's not too tricky. This number is a shorthand. This way of expressing numbers with powers, with exponents, it's a shorthand for write out the base is 3, write out the base 5 times in this case, and then multiply it out. We had to do this with polynomials. These are just numbers. How do you multiply them together? It's not too tricky. You just multiply these two first, and that gives you 9 times 3 times 3 times 3. And then you multiply these two together, and that gives you 27 times 3 times 3. And then you multiply these two together, and that gives you 681 times 3. And then you multiply those together, 243. Yeah? So my point is that this isn't actually all that difficult. There is an idea here, a shorthand. This exponential notation is a shorthand for a procedure. Write it out 5 times and then multiply them. Shorthand for a procedure. That's, well, I mean, all notation at the heart of it comes down to that. So that's all that means. It can be a positive whole number. You just write it out that number of times and multiply it. And this is why we were able to evaluate these negative numbers. Try this one out for size. Minus 2 to the 4 and minus 2 to the 3. We can evaluate both of these. They're cool. Write it out yourself and then telescope them. Multiply it by hand. So this is multiply these two together. That minus 2 times minus 2 is 4. 4 times minus 2 is minus 8. Minus 8 times minus 2 is 16. And this one. Minus 2 times minus 2 times minus 2. So the first one is minus 2 times minus 2 is 4. And 4 times minus 2 is minus 8. This is actually kind of neat. For this term, if it's 4, you get a positive number. It's 3, you get a negative number. That was fun. Okay. So in this list of different interpretations, we covered that one. You know how to interpret them. What about these other ones? Well, to get there, I mean, let's think about this here. When I was like, hey, we know how to interpret it, what we're saying isn't that there is anything new about powers. You see this power, and it's shorthand for a procedure. Write it out 5 times, and then multiply them together. Yeah? So this is a shorthand notation that we are interpreting. So the question here is, how do we interpret expressions like this? Like if somebody's like, hey, 3 to the minus 2, how do you write out 3 minus 2 times? Right now I've written 3 out 0 times. Oh, I wrote it out 1 time. How do I write it minus 2 times to multiply it together? How do I write it out half a time? Right? How do you write this number out 1/2 times so you can multiply it? Interpreting this doesn't make sense. Okay? That's the basic issue we have. Interpreting it for positive whole numbers, we totally have a system that makes sense. But the system doesn't break down for whole negative numbers and fractions. We don't know how to interpret it. That's the issue. Okay. So, the deal here is that various mathematicians over the years have come up with a sequence of arguments that lead up to a coherent interpretation. And I'm going to introduce you to those arguments. They're pretty fun. I 100% believe that you can follow them, but they have to do with algebra. Okay? They have to do algebra of exponential functions. Which is a big word, but essentially what I'm trying to say is 2 to the 3 times 2 to the 2 is equal to 2 to the 3 plus 2, which is equal to 2 to the 5. I know that you know how to do this. You had to be able to do it to do half of the stuff we saw ourselves doing in quadratics and multiplying things out, even polynomials. Question is, why does this work? How come I can add these two together, get that? And how come this number, whatever it is, times this number is equal to this number? I mean, we know that they are, obviously. I know you know how to do this, but why is that the case? Well, the reason can actually be sussed out by, let me write things in parentheses. There's a number, there's a number. I can calculate these numbers. That's 8, 4, 32, right? I can write the expressions in parentheses. I did just then. I'm doing it for a reason. This thing is shorthand for 2 times 2 times 2, right? How many terms are there? There's 3 terms, the number and the exponent. Write this term out. 2 times 2. How many terms are there? There's 2 of them, number and the exponent. So you can get rid of the parentheses because everything's just being multiplied together here. How many terms are there in total here? There's going to be 3 plus 2. There's 5 terms. So you can write this as 2 to the 5. That's literally the argument behind this, is that if you have a number to some power times same base, the bases have to be the same, of course, that makes sense. But if they have the same base, you can write the first one out as a times a times a dot 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 a times a times a. There are m of these, and then you multiply it by this one expanded out. A times a times a dot 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 a. I don't know how many there are here. There's n of them, right? And so overall, a times a times a dot 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 dot. How many are there in total? There's going to be a m plus n of them. So that's a to the m plus n. Okay? So the rule here is a to the m times a to the n is equal to a m plus n. It's a simple rule. I believe that you know how to do it. It's still worth exploring. See, oh hey, I should show you. 2 to the power 5. That's 32. So it's the same number as you would get multiplying it. But the point here isn't, hey, I found a better way to multiply to 32, because we have a calculator, so it's probably easier just to throw that in the calculator. The point here, though, is that there's a pattern. There's a pattern to the algebra, which is, if we have a term to an exponent, same term to a different exponent, if you multiply those 2 terms together, you can rewrite the answer as same base, these 2 added. Multiplication in the base is somehow equivalent to addition in the exponent, in the power. So why don't you try a couple of this? 2 to the 4 times 2 to the 3. Okay, here's what I want you to do. Write out and combine. Recombine into single exponent. And then 2, try the addition trick. Like I said, we're walking before we're running, so 2 to the 4 times 2 to the 3, write this out. 2 times 2 times 2 times 2 times 2 times 2 times 2. Get rid of the parentheses. 2 times 2 times 2 times 2 times 2 times 2 times 2. Count them up. Re-express them as a single one. There's 1, 2, 3, 4, 5, 6, 7. And then confirm. 4 plus 3 is equal to 7. Okay. So I want you to try these yourselves. Try this one. 2 to the 2 times 2 to the 5. And then 2 to the 4 times 3 to the 2. And then 2 to the 3 plus 2 to the 4. Try each of these. You can pause it, give it a go, so you can get your answer. So that's 2 to the 7 counted, which is equal to 2 plus 5. We're good. Oh, this one. 2, 2, 3, 4, 1, 2. Okay, how about this this one. 2 times 2 times 2. 2 times 2 times 2 times 2. Well, our trick worked in the first one. Hooray! It didn't work in the other two, and the reason is that the bases didn't match. So when I expand it all out, these are all 2's, these are 3's, I can't write those as just a big list of 2's. So I can't simplify it. Sad face. These are all 2's, the bases are the same, cool, 2, 2, 2, 2, 2, 2, 2. But I can't write them as a single, like 2 to the 7, because they're being added together, not multiplied. Okay, so this trick only works if the bases are the same and you're multiplying it together. Be super careful about that, please. So, following the evolution of mathematics, if you can add, you can also subtract, right? Add numbers, subtracting numbers, they're like opposites. If you can multiply, you can also divide, right? Well, in the last thing we covered, we were saying if you multiply the two terms to the two exponent terms together, exponential terms together, if you multiply these two terms together, that's equivalent to adding their exponents. So somehow multiplying is equivalent to adding. Can we say that dividing them is equivalent to subtracting? Is that going to work? Is dividing two terms equivalent to subtracting their exponents? I don't know. Let's try it. 3 to 5 divided by 3 to the 2. I'm going to write this out. 3 times 3 times 3 times 3 times 3 divided by 3 times 3. Okay, well, what's the answer here? 3 to the power 5 divided by 3 to the power 2. The answer here is 27. Cool, okay. So what? Well, when you write things out, you learned when you were a kid that you can in division like this, if things are perfectly factored, just multiply together. You can factor things out. Cancel these out. Cancel, cancel. And the result is just a bunch of 3 multiplied together. So it's 3 to the 3, which is equal to 27. But I want you to know why this is a 3. It's a 3 because there were 5 here, and we canceled 2 of them out. So this number is equal to 5 minus the number that you cancel out, right? So yeah, very much so. If the bases are the same, division corresponds to subtraction. Okay? So 3 to the 7 divided by 3 to the 4 should be equal to us going 3 to the 7 minus 4 is equal to 3 to the 3. A divided by m divided by n is equal to a m minus n. It's a pretty fun thing to use. Let's have you try a couple of these and explore. Try simplifying these. Write as a single exponential expression. That just means like 2 to the 4. That's what an exponential, a term with an exponent. So 5 to the 6 over 5 to the 3. Start by writing it out. 5 times 5 times 5 times 5 times 5 times 5 divided by 5 times 5 times 5. Reason it through. 5 to the 3. Cancel, 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 cancel. There's 3 of them left. And then check for yourself. 6 minus 3 is indeed equal to 3. 6 minus 3 is equal to 3. All right, try it yourself for these ones. 2 to the 3 divided by 2 to the 1. 4. Ooh. 3 to the 4 times 3 to the 2 divided by 3 to the 5. And 5 to the 2 divided by 2 to the 3. And 2 to the 3 minus 2 to the 2. All right, try these, write them out, simplify them, check to see if the subtraction rule is correct. Cancel, cancel, so that's 2 squared, and indeed 3 minus 1 is equal to 2. We're good. This is 3, 3, 3, 3 times 3, 3 divided by 3, 3, 3. 5. 1, 2, 3, 4, 5. So this is equal to 3 to the 1. 4 plus 2 minus 5 is equal to 6 minus 5 is equal to 1. Cool. It checks out. 5, 5 divided by 2, 2, 2. I can't cancel this. So I can't simplify it. Why not? The bases are different. What about this last one? 2, 2, 2 minus 2 times 2. I mean, huh? You can subtract those numbers, but it's not division. Stuff's not canceling. So you can't do anything unless they're being subtracted from each other. And you can't do anything unless the bases are all the same. But if you can, go for it. Okay, so that's the basics of combining exponents using multiplication and division. And it should have been a review. You should have been super bored during that. I hope you were. Okay, so next thing though. What if the power in the denominator is bigger than the power in the numerator? Let's write it out. 4, 4, 4 divided by 4, 4, 4, 4, 4. Let's play the cancel game. Cancel, 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 cancel. Huh. The result is 1 over 4 squared. Weird, because there's more in the denominator than there are numerators, so when I cancel them out, the ones left over are going to be in the denominator. But when I do the subtraction trick to this, it should be 3 minus 5 is equal to minus 2, right? So the answer here should have been 4 to the minus 2, but instead it was 1 over 4 to the 2. The reciprocal. Huh. The fact that these don't match and they don't make sense is actually the heart of interpreting negative exponents. Because here we have a negative exponent. How do we interpret it? That was the earlier question. How do you multiply something by itself minus 2 times? We have to recognize this is new ground. We don't have an idea of what interpretation to assign this, but we do know that if it's going to be consistent with this rule, this number should be the same as this. So that's how we interpret it. If you see a negative number in the exponent, the way we're supposed to interpret it is as the reciprocal, 1 over 3 to the power 2. That negative sign means take its reciprocal, go 1 over that number, over that base. It's a different base. Or alternatively, another way to think about that is if you see a negative number, write it as the number is in the denominator now. Negative numbers mean put it in the denominator. Negative numbers mean division. Negative numbers mean the reciprocal. Okay? So this is actually a pretty weird pretty weird way to think about it, but it's new. I'm not displacing my understanding of you know, 4 to the 2. Nothing has changed about the way we interpret if it's a positive number. It's just now I have extended my interpretation to include negative numbers. What am I going to do if it's a negative number? What you do is you go 1 divided by 4 to the power 2. Or alternatively, you write this as 1 over 4 to the power 2, the reciprocal. This is actually really cool. This idea, you flip it upside down, it's a really cool idea. And the reason it's a cool idea is it allows us to think of really different numbers, right? So 0. Say 5 to the power 3 and 2 to the power 4, okay. 2 to the power 6. Okay. So before, I might have said, okay, if I want to multiply these two together, you can combine them. 2 to the 4 times 2 to the 6 is equal to 2 to the 10 because they have the same base. Yeah? On the other hand, I'm stuck with the first one. I can't combine. I can't combine them together because they have a different base, right? Well, what this recent idea, this new interpretation for negative exponents lets me do is it lets me express things like this. 0 over 5 is 1 over 2, which is 2 to the minus 3. So even though this looks like a different base than this, if I allow for negative exponents and interpreting them in this way, I am now allowed to multiply expressions like this together. Combine them. What you do is you change the base, and then you write this as 2 to the minus 3 times 2 to the 6, which is equal to 2 to the 6 minus 3, 2 to the 3. Which is the same you would get numerically. Okay? So that's really neat. We've expanded the way we interpret the exponent to include negative numbers, and instead of making things more complicated, it's actually simplified the types of calculations I'm able to easily do. Now, there's one big question at this point in time. How do you interpret that one? How do you interpret this? How do you interpret this? What if it's a 0 in the exponent? Well, the answer, you know that the answer is 1. You know that the answer to all these are 1. They're all equal to 1. But do you know why? The reason comes about from the interpreting of terms that we've already talked about. Because look, 2 to the 4 divided by 2 to the 4. What's that equal to? It's equal to 1, right? But 2 to the 4 divided by 2 to the 4 can be written as 2 to the 4 minus 4. Can be written as 2 to the 0. Similarly, 3 to the 7 divided by 3 to the 7 is equal to 1. You can rewrite this expression, though, as 3 to the 7 minus 7, or 3 to the 0. The very reason we interpret all these numbers as being 0 has exactly to do with our interpretation of subtraction in terms of division. Division means subtracting exponents. Our new interpretation of this allows us to interpret 0 exponent terms as equal to 1. That's the reason why we say those numbers are equal to 1. Isn't that fun? So, to add one more piece to the interesting pie, think about it like this: a to the n divided by a to the subtraction, right? If I want to, I can write this as, all right, before we go on, hold on. 4 divided by 7. If you want to, you can think about division in terms of multiplication, where the denominator has been turned into like this reciprocal expression. We can do the same thing in terms of exponents, right? So you can say that this division algorithm corresponds to a multiplication algorithm. You can say that the second term is equivalent to going a to the minus n. And then you can say, hey, look, this is, I'm multiplying two terms with the same base, so I can add their exponents. And that's cool. Yeah, look how cool it is. Because now, instead of thinking about this as just adding two numbers, this one here is a negative number. Addition of a number with a negative number is equivalent to subtraction. Yeah? See how it all fits together? That's pretty cool. Okay, so let's review what we've talked about so far, because there's a lot of material. A to the p. A is called the base. It can be any term. Wait, not almost any number. Sometimes not any number. This p number, though, is called the exponent. This is, you know, for any specific number, it's something your calculator can figure out the answer to, but you can figure out the answer to it as well, independently of your calculator. And the idea is that you have to interpret it. The calculation you do depends on your interpretation of the number, right? So if p is a whole positive number, like 1, 2, 3, you know, just multiply a times a times a times a. Multiply it p times. If p is a whole negative number, like minus 1, minus 2, minus 7, right? Divide. Or, you know, so go 1 over a times 1 over a times 1 over a, 1 over a. Multiply its reciprocal. If p is equal to 0, then you say a of p is equal to 1. Okay, so all of these ideas came from a sense of the rules for algebra for the exponent terms. If you multiply two terms that have the same base, you can just add their exponents. If you divide two terms with the same base, you subtract their exponents. And if you want to, you can talk about multiplying them if they're negative, you know, and in that case you would be like an plus minus m. And as long as you accept the existence of negative numbers, that makes exactly the same sense as that. Some people don't think negative numbers exist, though, so if you don't, I mean, you can stick with operations. Okay. So that's what we've talked about so far. I hope it made sense to you, because we're going into new territory, which is, what if p is a fraction? You know, you can multiply something a whole number of times. You can divide something a whole number of times. How do you multiply something half a time? Like, okay, so 10 to the 1/2, is that like there's half my 10? I've written half a time. Is it 5? What do we do? There's no way to interpret it. You can't do something a half number of times. So that's not how counting numbers work. So before you go on, your calculator knows how to do this. So you can go 2 to the 1/2, or you can go 9 to the 1/2, or you can go 8 to the 1/3. 2 to the power, so 2 to the power 1/2. That's equal to 1.4142. Like, what's that number? I don't know. But it's just some number. 9 to the power 1 divided by 2. That's equal to 3. Oh, it's a whole number. That's weird. Alright, so 8 to the power 1 divided by 3. What does that give me? Oh, that gives me 2. That's a whole number too. Well, that's very interesting. At this moment, if you're champing at the bit and saying, oh, they're equal to roots. They are equal to roots. Do you know why they're equal to roots? Just like how the trick to interpreting negative exponents came down to building a sense of algebra in the system, looking for patterns in the algebra, the same thing goes for interpreting fractional exponents. So, how do we do that? The rule goes like this. It comes down to the rules involving interpreting expressions like this. I wonder if anybody's watching. Oh, one person's watching. It's probably me. I'm probably the person watching. Okay, so how do you interpret that? Well, at first it's really weird, but if you think about it in terms of function notation, in terms of operations, this makes a lot of sense. What we're saying is, take this thing in the parentheses and multiply it by itself twice. 2 to the 3 times 2 to the 3. I know how to do that. Okay, so is smart Alec, try this one. That's equal to 5 to the 7 times 5 to the 7 times 5 to the 7. So that's equal to 5 to the 7 plus 7 plus 7. So that's 5 to the 21. I want you to see something pretty cool here, which is that 6 is equal to 3 times 2. 21 is equal to 7 times 3. That's not a coincidence. The reason it's like that is because this term here says multiply this out 3 times. Right? Each of these terms is identical. 10 to the 7. So there's 3 terms being added together. These are all identical. 3 times, that's equivalent to multiplication. 3 times 7. Okay? So generally speaking, if you ever see an expression like that, you can rewrite it, recalculate n times m. So try one of these. Try some of these yourselves. 2 to the 3 to the 4, 2 to the 2 to the minus 3, 3 to the minus 2 to the 4, and 4 to the minus 2 to the minus 3. Write each of them out, count them out, and then make sure that that rule I told you. Okay. This first term is 2 to the 3 times 2 to the 3 times 2 to the 3 times 2 to the 3. So that's 2 to the 3 plus 3 plus 3 plus 3. So that's 2 to the 12. And 3 times 4 is equal to 12. What if it's negative? That's equivalent to us going 1 over 2 squared times 1 over 2 squared times 1 over 2 squared, which is equal to 1 over 2 to the 2 plus 2 plus 2. They're all in the denominator. So that's 1 over 2 to the 6, which is 2 to the minus 6. Minus 6 is equal to 2 times minus 3. Hey, it works. What about this weird one? You go like this. 3 to the minus 2 times 3 to the minus 2 times 3 to the minus 2 times 3 to the minus 2, which is equal to 3 to the minus 2 minus 2 minus 2 minus 2, which is 3 to the minus 8. Yeah, check it. Minus 2 times 4 is minus 8. Cool. Last one. Oh, this one's weird. 1 over 4 to the minus 2 times 1 over 4 to the minus 2 times 1 over 4 to the minus 2, which is equal to 1 over 4 to the minus 2 minus 2 minus 2, which is equal to 1 over 4 to the 6, minus 6. Oh, weird. This is 1 over 4 to the 6, which is equal to 4 to the 6. Oh, neat. Hey, look. 6 is equal to minus 2 times minus 3. The negative signs cancel out. Hey, it works. It works. So, the rule here is, this is powers. Our exponential term to a power corresponds to multiplying the exponents. That's neat, right? Okay, I think you know how to do that. Ready for the fun part? So there are situations where we multiply exponents. Are there situations where we divide exponents? You know, like that? Are there situations where we'd be like, a to the 4 divided by 3? Well, I mean, yeah, but like, when, huh? Let's think about division in terms of multiplying reciprocals. Right? We mentioned that one earlier. So instead of saying 4 divided by 4, what we could say is 4 times 1 over 4. That's equal to 1. Yeah? So arguably, 2 to the power 3, 1 over 3 should be equal to 2 to the 3 times 1 over 3 should be equal to 2 to the 1. Right? Yeah. Yeah. So it seems like there is some situation where you would want to have a reciprocal exponent. But how do we interpret that? Call it fraction. just because we used reciprocal already in the thing. So things with simple fraction exponents, like, so if I was like, 4 to the 1/2, what is that? Well, I know that 4 is 2 to the 2, right? And so arguably, this value, whatever this 1/2 is, it should give me like 2 to the 2 times 1/2, so 2 to the 1. Do I have a procedure? Like, do I know of any function where if I plug in 3 to the 2, I get back 3? Or if I plug in 4 to the 2, I get back 4? That's what we're talking about. We're talking about a function where you plug in something to the power 2 and you get back the thing. I do. The inverse. Right? Yes, it all comes together. Square root. We know that square root of 2 to the 2 is equal to 2. You know that square root of 3 to the 2 is equal to 3, right? It's the square root. It inverts the squaring procedure. Yeah? So, here's the fun part. The square root inverts the squaring procedure. It seems to me, according to the algebraic arguments that I've seen before, that putting something to a fractional power like that should also invert the square in this case. You see where I'm going with this? Roots represent square roots. Fractional exponents. If you see a fractional exponent, it means it's a root. Interpretation. According to the arguments that we've seen so far, the algebraic arguments, if you see some number to 1/2, it's a shorthand. It's an algebraic shorthand for plug it into the square root of your calculator. So 9 to the 1/2, that means plug it into your root calculator. Okay? And furthermore, I mean, you can be like, how do you interpret 1/3? 1/2 is a square root, right? Well, 4 to the power 3, if you put 4 to the power 3 all to the power 1/3, according to that multiplication rule, you should get back the 4. 4 to the 1, it's just 4. So what operation inverts the cube? It's the cube root. So this operation and this operation must be the same thing. They give you the same output for the same input, so they must be talking about the same thing. So anytime you see a number to an exponent, a simple fractional exponent, 1 over a number, that's equivalent. We're telling you to take out your calculator and take the nth root of that. That's super fun. Okay, so this is actually something you've seen before. You've definitely seen me write out this as 1 over n. You've definitely seen me write this as 9 to the 1/2. I've definitely done it in class. That's because expressing roots in terms of fractional exponents is computationally a lot faster than expressing them as square roots. You can do a lot more, a lot quicker. Let me explain what I mean by that. I mean that if somebody goes, okay, 7 to the power 4 square root. Evaluate this, please. Ordinarily, you would have to do it in 2 steps. First, you'd have to calculate 7 to the 4, which is some terrible number. Right, hold on. Forget what I just said. Okay, so somebody goes 7 to the 4, and you want to calculate that. Ordinarily, it's pretty terrible. You'd have to first calculate 7 to the power 4, which is 2401, and then plug that into the square root of your calculator. 49. This is actually a much faster way to do it. If somebody tells you 7 over 4, instead of writing the square root using this symbol, express it as a fractional exponent. So I want the square root. And then you can use your multiplication rule. So that's 4 divided by 2 is 2, and 7 squared is 49. Yeah? This shorthand has become a tool that actually speeds up paper computation by quite a bit. Okay, so what about a mixed fraction? So if somebody's like, hey, 3 to the 4 over 5, how are you supposed to interpret that? Well, one idea is you interpret this, like if somebody tells you to put this in your calculator and you don't have the type of calculator where you don't have a decent scientific calculator, what are you going to do? Well, the deal here is you can think of this either as 3 to the 4, which corresponds to the 5th root of whatever 3 to the 4 is. Figure that out, calculate that numerically. Or you can think of this as up to the power 4. It doesn't show up very often, but sometimes it does. So the deal here is that we can interpret mixed fractions in terms of this multiplication rule. Break it up into 2 pieces and think of each piece as its own procedure that you have to evaluate. All right, so let's review. A to the power p. If p is a whole positive number, just write it as a times a times a times a. Just multiply it out p times. If, on the other hand, p is a negative number, like minus 5 or something like that, you would write it out 1 over a times 1 over a times 1 over a times, you do that p times. Right? So you can compute that. If p is equal to 0, you know that a to the p is equal to 1. But now we also have an additional interpretation. If p is a simple fraction, go figure out what the nth root of it is. And if p is a mixed fraction, first take the nth root of it, and then take that number and multiply it by itself n times. So that's great. This has been exhausting, but it's actually fairly useful. And it's useful for a type of calculation I want you to learn how to do, in part, well, mostly just because it's really good practice to get these rules down. And so the procedure looks like this. I'm going to give you an expression like this. 6 to the 2 times 6 to the 3 times 3 times square root 6. And I'm going to say, note that 6 is equal to 3 times 2. Simplify this. Okay. Let me show you how it's done. The deal here is that we can express this whole thing in terms of exponents, and then using the algebra of exponents, we can boil it down into a simpler expression. So the first term is 3 times 2 to the power 2. The second term is 3 times 2 to the 3, all to the power 1/2. Down below, it's 3 to the power 1. And then it's 3 times 2 all to the 1/2. And now we just expand. 3 to the 2 times 2 to the 2 times 3 to the 3 over 2 times 2 to the 3 over 2. You know what? Maybe I should do that as an intermediate step. So then this becomes 3 to the 3 times 2 to the 3, 1/2, all divided by 3 to the 1 times 3 to the 1/2 times 2 to the 1/2. So this becomes 3 to the 2 times 2 to the 2 times 3 to the 3 over 2 times 2 to the 3 over 2 divided by 3 to the 1 times 3 to the 1/2 times 2 to the 1/2. Alright, so then you get 2 plus 3 over 2 minus 1 minus 1/2 plus, no, times 2 to the 2 plus 3 over 2 minus 1/2. Hey, you're very good at adding fractions. You can do this part on your calculator, I don't care. 2 plus 3 over 2 minus 1 minus 1 over 2. So this is 3 to the 2 times 2 plus 3 over 2 minus 1 over 2. 2 to the 3. So that's 9 times 8, which is 72. Okay. So in this calculation, what you do is you're given something weird like this, you do a replacement, and then you use the rules of exponential algorithms, or the algebra for exponentials, to boil it down to something simpler. Okay. Note that 10 is equal to 2 times 5 and simplify. So the first term becomes 2 to the 1/2, and the second term becomes 2 times 5, 4 over 3, and this term becomes 2 times 5, that's the 10, 2 over 3, and the denominator becomes 2 times 5, 3 over 2, and the last term is 5 to the 1/2. So this becomes 2 to the 1/2 times 2 to the 4 over 3 times 5 to the 4 over 3 times 2 to the 2 over 3 times 5 to the 2 over 3 divided by 2 to the 3 over 2 times 5 to the 3 over 2 times 5 to the 1 over 2. 2 1/2 plus 4 over 3 plus 2 over 3 minus 3 over 2 times 5, 4 over 3 plus 2 over 3 minus 3 over 2 minus 1/2. 1/2 plus 4 over 3 plus 2 over 3 minus 3 over 2. It's 1. 4 over 3 plus 2 over 3 minus 3 over 2. 0. Oh, so the answer is 2. See how that works? Okay. long story short, this is a technique I kind of expect you to know how to do. Mostly I expect you to know how to do it already. Hopefully if you learned a little bit about combining exponents a little bit, that kind of stuff, I hope that this is mostly a review for you. But to conclude, let's medicine wheel this thing. The bulk of our focus wasn't just on exponents, wasn't just on interpreting what the number up here could mean. That was a big aspect to this lesson. What does that number up there mean? How do we interpret it? But our interpretations, our assigning meaning to whatever that number is, comes down, in essence, to a set of rules involving exponents. If I have two terms that have the same base and you multiply them together, you can add their exponents. If you have two terms and you divide them, you subtract their exponents. If you have a term and it's multiplied to, it's put to a bigger power, a different exponent, you can multiply the two exponents together. And if somebody gives you a mixed fraction, you interpret this as the nth root of your base to the power m. Okay? So all of this comes down to how to interpret these numbers, the algebraic rules relating multiplication to addition, relating division to subtraction, relating to powers to multiplication, and relating roots to division are a huge aspect of exponents. And what this apparatus has let us do is it lets us interpret when somebody gives us an exponential function. Okay, that's it for this huge video. I hope it was super easy and I hope it was super boring for you. I'll see you later.